So let's see. Okay, we will start now. So today, in the first, I would like to remind you what we did in the previous lecture. So this is we consider it covariant derivative, and we discovered that in the general case in curve space the derivative is different than in the flat space. As a result, we obtained some new object, which we call, here you can see, which we call Christoffel symbols, and which depend on the metric of the space, of the metric tensor. Finally, we obtain this expression. And in principle, these Christoffel symbols, they have an information about the space. But unfortunately, as we also discovered, this mathematical object, this is not a tensor. It's why we call it symbol. And it's not convenient to us because I also would like to remind that our main goal to obtain the equation of gravity such a way that this equation will be the same in any coordinate system. This is the point of general relativity. And as we already understand, it means that this equation should be a tensor equation. And we also need to find the object which from one point can see the information about curve space and curvature of the space. From another side, this object should be a tensor object. So this object need to have a property of the tensor. And this is exactly what we will do, and we will discover these lectures. Sorry. So let's write the title of the lecture. This is Riemann curvature tensor. So I also promised you in the previous lectures that we will work a little bit with the Christoffel symbols for some examples of the space, and we will do it a little bit later. We will consider and we will find the component of Christoffel symbols for some simple case, and after this you will obtain the home task to work and to obtain the Christoffel symbols for another cases. But I hope we will have a time at the end of this lecture, so I will consider it a little bit later. And now we will concentrate with this new object, Riemann curvature tensor. So it's very important because if we would like to know is the space is really curved or not, this is exactly this information can give us exactly the Riemann curvature tensor. And as we will see, this tensor, tensor is a 4-rank tensor, but finally, as you will also see, finally we will work with, as I promised, with the 2nd-rank tensor in the Einstein equation. So in the beginning, again, I would like to remind that, so if, for example, we have a flat space or Cartesian coordinate system, so Cartesian coordinate system, as we understand in this case, the metric tensor, as we discovered before, this is just unit tensor. So this is 1 when I equal k, and 0, 1, I doesn't equal k. So, and in this case, all Christoffel symbols equal 0. Just to remind and to put an idea how we can find the Riemann-Curvature tensor. And to write what I said before in your conspect. But okay, we write that gamma is not a tensor. So from this point, we need to find some object which is a tensor and which can describe the curve space, the curvature of the space. What we know, we also know that in Cartesian coordinate system or in a flat space, just a second, I would like to. Somebody forget to switch off his microphone. Please switch off your microphone. Thank you. So if we are, I might say, in a flat space, or from the point of coordinate system, we are in Cartesian system. Coordinate system. What we know? We know that if we have a double derivative, so if we, for example, I have some function, and just a second, I have a call. I'm sorry, I come back. So if we have some function and we consider the second derivative of this function, for example, I can consider the operator such a way that d by dx I, d by dx j, which apply to this function. So doesn't matter, we can put it, doesn't matter the order how we are doing this. So we can also write like this, d by dx j, d by dx I, f. Oh, it's understandable. So we can write d to f, x I, dx j. So, or if we will take into account our notation, when we use comma as an indication of simple derivative, particular derivative, so we can write that f I k, sorry, we will use j, equal f j I. Sometimes we can just to put f j I. It means that we already put the second derivative. So it's like this. But if we will take into account this, what we have in a flat space, and what we know from mathematical analysis. But as we could see before, when we consider the general reference system, including which can be related with the curve space, our operation of differentiation is really different. It means that, again, I will move here just to remind you. So here you can see that operation of differentiation is really much more complicated, because we have additional summand which take into account of the fact that when we have a vector and we move this vector along of coordinate axis, this vector will a little bit rotate. And due to the fact that coordinate system is not, coordinate system and coordinate axis can be curved. And as a result, this information about coordinate system we have exactly in Christoffel symbols. So it means that if we are in general case, for example, in curved space, in this case, we need to, I will write here, general case, and I will indicate it as a curved space. We, instead of already just derivative, we need to put point and comma, okay? Which we remember that it means this is covariant derivative. And if we will write now, for example, if we have some vector and we consider now the more general case, this is covariant, the second covariant derivative from this vector. So I will write like this, L, K, minus K, L. So you can see that I change just an order how I take this derivative. So this case, this final expression will not equal 0. So in a general case, the operation of general case, this is covariant differentiation. In this case, the operation of covariant differentiation is not commutative. You can write it in your conspect. Operation of covariant differentiation is not commutative. So, and if we will consider this operation, we will see how in this case we will obtain Riemann curvature tensor. Let's do it now. And to do it, I will move on the second page. To do it in the first, we need to remember the expression of covariant derivative of the tensor of this first rank and of the second rank. So the first, I will write it here because it will be convenient to use immediately. So if we have a vector, which is a tensor of the first rank, so, and we would like to find the covariant derivative by coordinate x with index L. So what it will be, it's just a particular derivative, as this one, plus, just a second, for 1 second, because excuse me, it's some very urgent call. It was urgent call. So plus Christoffel symbol, the construction such a way that we need to put Christoffel symbol and and the corresponding vector. So now we need to distribute the indexes. So we remember that gamma take index I, which is above. After this, gamma also keeps the index L, and here we need to put summation index M and M. So this is what we obtained before, and we know this very well. Also, we will need, and we will put here, and I will, I just want to say that, okay, later we will consider, but now I will put like this. So, for example, we have a tensor of the mixed tensor of the second rank, index I, index L. And covariant derivative K equal T I L, just a derivative, plus, and after this we write the construction, gamma T minus gamma T. Now we need to distribute the indexes. Please check everything, not to make a mistake here. So here for this part of the top index, the index which above, so with the contravariant component, we need to take here I, here K, and summation index P, and here we put the final index L. Here, otherwise, gamma take the low index L, K, and here P, and here P. And after this, we need this P summation index. I put I. Okay, this is what will help us to obtain finally Riemann tensor and to work with with this operator, which we can write here, what we would like to find. So we would like to find what it will be if we will consider the operator like this. AI, covariant derivative L, K minus AI, KL. So this is our goal. Okay, let's do it. Just a second, I would like to check that nobody doesn't ask to come. Okay, everybody here. So in the first, I will consider this one. L, K. Okay. So what it means? I will use for this first part exactly expression which we know for covariant derivative. Okay, and we understand that finally we have a tensor and we can apply the operation of covariant derivation to the tensor. So it means that I can write like this. So I use this one and I write AI derivative L plus gamma I ML AM covariant K. Please, if something you don't understand, please ask me. So, and after this, since finally here we have a tensor of the second rank, okay, so because after applying of the operation of covariant differentiation to the vector, we finally will obtain the tensor of the second rank. So we can consider this one. I will put here arrow. We will apply the law which we are using exactly for the tensor of the second rank. What it means, now it will be understandable what I will do. So the first, I need to put just a particular derivative of this summand. So it means that I just need to do like this. Plus, after this, I need to consider the second summand. So I put here as a term, as a multiplier, Christoffel symbol, pk. And instead of this tpl, I will use this one. But instead of I need to put p. So I write AP L plus gamma P M L A M. So as you understand, I just take this one, but instead of I need to put P. Okay, now I come back. Continue. So minus. Now I need to write the final term minus. So I write gamma P L K, and I need to put again what is in parentheses, but instead of L, I need to put P. So it means AI derivative P plus gamma I M P A M. Here we need to be very careful with the indexes, because if we will make a mistake with the index, so fine, of course, we will not obtain what we want. And we can control to consider the summation index that finally, so we start, I will start from this one, okay? So, and we have from the left part indexes ILK, which should be again kept on the right side. And in principle, if you look, so this is like this. After this, we need just to open parentheses. So, and the first one, it means that we have I derivative L derivative K plus here derivative from the product. So it means that we can write in the first IAM derivative K. So I'm working now with this first term. Gamma IML plus AM, and I even write like this, D gamma IML by DXK. This is the second, this one. Now we will consider this one. Just need to open parentheses. So we will have plus gamma IPK APL plus gamma IPK gamma p m l a m. And the last one, this one. Okay, so we have a minus gamma p l k a I p minus gamma p l k gamma I m p a m. So it's all enough long, but now we will enjoy the situation when we will kill a lot of summons, because now I will consider the derivative like this. But I change the places of L and K. Okay, the first covariant derivative by K and the second by L. But we immediately can write the final expression. So I will put this equal this. Okay. So because I just need to look what we obtain here and just to change K on L. Because it's looks like just recalling of the indexes. So we will not do something wrong with this. It's exactly what we can do. So let's do it. I will look on the first sum on this one. So I just write A I K L plus AM. If you don't understand something, please tell me. Now it's understandable?
Yeah, understandable.
Good. Okay, now instead of K, we put L. I just rewriting I, M. Instead of L, I put K. Plus A, M, d gamma I, M. Instead of L, I put K. dx, instead of K, I put L. Plus gamma IP, instead of K, I put L. AP, instead of L, K. Plus gamma I, P, L, gamma P, M, K, A, M, minus gamma P, K, L, A, I, P, this is the same, minus gamma P, K, L, gamma I, M, P, A, M. Let's look that we write everything. And now much more pleasant part. So now we will write. I will put it. So what finally we will have from this operation, if we will consider this one, equal. So we don't need to rewrite everything. We can look on the first, this one, and on the second, this one. So I will compare, I will put it here also to look more convenient on this summand. Okay, and I now will just to kill the summand, which will disappear because they are the same. So the first summand, this one here, oops, sorry, the first summand here and here. This summand are the same or not?
Same.
The same. So we can kill it. Now consider the second summand. this one. And let's find, can we find here in the second expression the same summand? Let's look on this one. What do you think? They are the same or not?
Same.
Yes, they're the same.
Yeah, this is the same because M here, this is summation index. And we can put any indexes. We can, instead of M, put P. And this is also summation index. So they are the same. So we can also, when we will consider the first one minus the second, so it will disappear. Okay, this one. Let's find this one on the next expression. Mm-hmm. What about this one?
I don't see this one, but I think I found the component before this.
This
that
one,
you-
you mean?
Yes, but I can make mistake, but I think yes, I see such component in the
Yes, it
that-
looks the same. Jose, it looks the same. Which is your name?
Vlada.
Vlada. It looks the same, really, but it's not completely the same. Because you can see here that, for example, in this summand, I will put now the different color. This one, in this one, they are looking by structure the same. But we need to be careful because the derivative here on the different indexes.
Oh yes, yes, I see.
Yeah, so in this case, we can't use it, but in principle, by structure, yes, they are similar. But now I would like to make an attention about this next summand, this one and this one. What do you think? They are the same or not?
No, they're the same.
The same, of course, because again, here we can, now you can feel it, that the same. This is when the summation index only is the same, but others index are not the same, can be not the same. Sorry, I said the stupid thing. So otherwise, the summation index can be different, but others indexes, they are the same. So M here, and here P and P. So this will also, let's put like this. So they will also disappear. And I think we can find the last one. I will put this one and this one. They are also the same. Again, with the same rule. And also we take into account the property of Christoffel symbol, which we found and which we discussed before, because the Christoffel symbols are symmetric relative to permutation of the lower indexes. Okay, so it means doesn't matter gamma k L or gamma LK. So these two summand also will disappear. Let's put like this and like this. And also we can see, sorry, you know, it looks like but we did everything a perfect way, just a lot of color. But now we can collect everything. And also we can see that we have everywhere in a final summand, which will be not disappeared, which we will have. Everywhere we have AM here, AM here, AM here, and correspondingly here, here, and here. So we can take out it from parentheses and collect all summands which in front of AM. So finally, I can write this. I will kill. I can write the following. What we have, so I can put in the first. AM. Okay. And it will be not beautiful. I will write much more compact way. Don't kill everything in your conspect. I just will write it more compact. Sorry. Okay. A I L K minus A I K L equal. So I will put AM here and will write everything what I will have in parentheses. I will have d gamma IML by dx k minus d gamma, this one, IMK divide on dxl plus gamma IPK, gamma, this I write this one, gamma PML minus, and I write this one, gamma IPL, gamma PMK. And we can put it in some frame. Okay, green frame. This is final expression which we obtain. So let's call what we obtain here as put some letter R, and we can see that finally we will obtain some question.
Yes, only one question. So
yes, ask question.
Yes, maybe one question about why we can remove two terms which we marked by red dots under them. So we do not remove them. I think that we
No, we don't remove. I
need to
just
have. Okay, so I think we need to have two more terms because we have 7 in each expression,
yes.
and
Yes,
and
right,
we kill
right.
only 4.
We need, yes, thank you, yes, you're right. Because we forget about, thank you, yeah. I forget about these two. This one, this is, and this one. And they are also the same. We just forget to kill them because it's immediately you can see that they are the same. Agree? Are you agree? Now.
Agree.
Agree. So because I immediately, yes, agree. You immediately can see that they're the same due to the fact that gamma LKK, I forget to kill it. Sorry. equal gamma p k l. Due to this fact, this summand also disappeared. And we have in this parentheses only 4 summands like this. So now I think everything we did with the right way. But thank you that you check everything, because of course it's very important not to make a mistake here, because in the next step when we will write Einstein equation and we will work with the next step, so it will be important. I will call this, what we obtained, I will call it R, and this object which we obtain here in the parentheses will have how much indexes? What do you think?
Still 3 indexes.
3? Why 3?
Yes, only I, L, and maybe we have 4th index M.
4, yes, exactly, 4. So the index above contravariant will be I and M, K, L. So I can write what you write above, I can write like this. Equal A, I, L, K minus A, I, K. And this object which we obtained, this one, this called, this exactly called Riemann-Curvature tensor. Curvature tensor. So I will, you can rewrite it, but you can put it in your conspect. I can put on the next page. So here, because it's important that we will use it. So R, I, M, M, K, L equal. And we understand the construction. So the construction such ways that we need to put in the first terms. This is derivative from the gamma symbols. And I will distribute the indexes a little bit later. Plus gamma on gamma minus gamma on gamma. So, and now I will put indexes. And the first, let's take 2 indexes ML here, and the index K here, and I put I here. The next, I need to take MK in the first, and final index L here, I. The next summand, the first gamma, gamma take K, in the second L. Here ML, PPI, and after this MK, PL, PI. So this is expression for the Riemann tensor, which you can see not so simple, but don't be scared, because finally we will work, as I already said, with the tensor of the second rank Einstein equation. What is important? That
I'm sorry,
yes,
can I ask one question?
yeah, of course.
Maybe here we should write M LK, or it must correspond to derivative which stays after minus, or corresponds to first. No, this
LK,
order of letters. So we have
yes,
first derivative
now I try to
LK.
check, so it should correspond exactly what we obtained here.
So if we
Gamma
have LK,
IML, gamma MLK, MKL, and yes, PK ML.
no, the expressions are the same.
Yes.
I have questions only about the order of letters, order of indexes in R. So just KL or LK?
Now for now we can now here MKL. Later, when we will consider the properties of Riemann tensor, we will see that it's symmetrical or asymmetrical relative of the permutation of the indexes. And we will understand how it will appear minus or will not appear. But this is right, this is correct for now. Because I can say in advance that Riemann tensor is symmetric relative to permutation of the pair of the indexes. So in this case, doesn't matter, KL or LK. But it's asymmetric respect to another permutation. So, and it will appear as a minus, but we will see it a little bit later. So this is right. So we can, and in principle, we put here the first KL, so it's a notation like this. If we will put here minus, so it means that we need to put minus in other things. So this is definition of Riemann tensor. So I answered on your question.
Yes.
Okay. So, and what is important, you can see that I start to call it as a tensor. And of course, you can ask me, but we are sure that it's really a tensor. So this object transformed from one coordinate system to another as a tensor. Of course, we can check it. We can, consider the passing of this tensor from prime coordinate system to non-prime coordinate system. But we can look on this final expression, and we understand that from the left, from here, from the left side, we have a tensor, because this separator of covariant derivative make from the tensor, make a tensor. So this is also tensor, because we agreed that this is vector, and vector, this is tensor of the first rank, and we proved that this vector is transformed as a tensor. So it means that this is also a tensor. So we also can, and sometimes much more convenient, that consider the to make the index lower. So if we will apply, for example, to the, I will come back to the blue. If we'll consider, and yes, and what is also important, this is a tensor of the fourth rank, because this tensor has 4 indexes. And it's understandable that if we will need to find the covariant derivative from the tensor of the first rank, it means that it's a really complicated business, because we need to put many sums. But fortunately, we will not need to do it, because again, everything will be more simple in for us in general relativity. So now I want to, this is, as you understand, the expression for the Riemann tensor in mixed form, because we have one contravariant component and three covariant component. But if we would like to work with only covariant component, in this case, we can apply the rule of lowering of the index as to each tensor. So we need to put here symmetric tensor. And for example, I will put here I don't know, n. So, and finally, I will obtain R, N, M, K, L. A little, I would like also to speak a little about geometrical sense of the Riemann tensor, this curvature tensor. So why we really, so, and you can see, and you can write in your conspect that Riemann tensor, Riemann curvature tensor, appear due to the fact that operation of covariant differentiation is not commutative. Is not commutative. So, and we will see it from this procedure which we did before. About geometrical sense of this, let's put it. Geometrical sense. Why it's like this? So we can consider this on an example, much more simple space. So consider two-dimensional space. Two-dimensional space, and two-dimensional space curve, the more simple curve two-dimensional space, this is of course sphere. So if we will consider sphere, okay, I will try to use this one. Okay, so, and on this sphere, I can, I would like to choose some contour. For example, this one, okay, like this. So, closed contour. For example, for the flat space, if I will consider some closed contour like this, and I will put some vector, and I will pass this vector along this contour. So this is, for example, AI, and after this I will, sorry, I will, it doesn't work. Okay, it's not so beautiful. So, and I will consider the parallel passing of this vector along this contour. So what I will do? I will do like this, I will do like this, okay? And finally, we understand that this vector will come back to this point in the same place after all of this procedure, when we will go to this contour. And this is in the flat space. But if we have a curved space, so, and let's do it. You can keep it, just for me the space is not enough, so I will put it bigger. like this. Okay, so this is like this is like this. I just will draw some closed contour, which I choose on the curve surface, which is, can be, for example, the surface of the sphere. So what I will see, if I have the vector here, I will start from this point. And this is the vector AI. If I will move this vector and come with this vector in this point, the parallel passing along this contour. So it will be like this here. After this, I pass from this part of the contour. Okay, so and vector will be here. This is the first point, the second point, the third point. And finally, if I will, of course, this is schematical, if I will pass it from this point, so it will come back here. So we can see that the final vector, if we will pass it along the close contour, will not come back in himself. And this is the point, and this is exactly the information. It tells us that the space is not flat. So if this is a flat, it's come back in himself. But it's not a flat, so it can change the direction and orientation and direction. And this is exactly the information which consists in the Riemann tensor. So this is geometrical sense. It looks like the same, the similar, which we discovered for covariant derivative, because as you remember also, due to the fact that when we consider derivative, we also need to move the vector in the point vicinity, the vicinity point. We have the same problem, because due to the fact that coordinate axis is not straight, when we pass the vector, it will be also a little bit rotate, and as a result, we obtain this additional summand, which consists of Christoffel symbol. So this is geometrical sense, and also there is a very important, theorem, so which tell that the Riemann space is we can say more simple way. The space is flat only when all component of Riemann tensor equal 0. So it means, again, not to be confused, because if you have, for example, Christoffel symbols, which can be 0. So, but we need to be also careful that to be sure that the space is a curve, you need to check all component of the Riemann tensor. So, but we will work a little bit with this. But exactly on this part, I think it's more convenient. So, by the way, I received the solution of the task home which you needed to do. Thank you. I will check it and will take into account for the final mark. But now I would like, as I promised before to go to the properties of the Riemann tensor, I would like a little bit to work with Christoffel symbols. just to, you know, to play with this, that you will feel that it's not so complicated as it looks before, and you will have your home task to calculate also the components of Christoffel symbols. So later you will also will have a home task to calculate, for some example, the component of the Riemann tensor. Example for some metric for calculation of Christoffel symbols, because as you understand here, to obtain the component of Riemann tensor, we need to know the component of Christoffel symbols. And you know, when we will reach Einstein equation, and when we will work with the metric of our world, I mean, it's a cosmological metric, you will see how we can calculate everything considering of the metric of our world. So this is just to make you much more interesting in this point. Okay, the first one. The first one, I don't remember, it looks like we didn't consider, so consider the Minkowski space. Minkowski space, interval for Minkowski space, this is c dt square minus dx square minus dy square minus dz square. Nothing incredible. So the metric tensor, again, I will remind that in this case, x0, this is ct, x1, this is x, x2, this is y, x3, this is z. And the metric tensor, which we have, g, if we will consider this like gik dxi dxk, we can immediately to write metric tensor, which is, what is this? This is constant. Yes, this is 1, minus 1, minus 1, minus 1. And as we discussed before, I will put 0 like this. So everywhere we have only diagonal element. Let's remind what is a Christoffel symbol, which we obtained here. I will write invent some indexes. For example, just remember this by heart. I hope IKL. So Christoffel symbol is 1.5. G take the index I. Okay, and now I put summation index. After this, I remember the mnemonic rule, because the G take the first index K here, and after the summation index L, plus GK the second index L, and after the summation index and last index K, and minus J, and in this sum and G take two indexes KL and summation index M. So like this. Or if you would like to write it's the same, it means GKN dxL plus dgln by dxk minus dgkl for dxl. So this is the same. Just to remind that this comma which we have, this is means that L, for example, dxl. Okay. So summation index, it means that we need to make a summation. So summation index, I again would like to remind you, due to Einstein summation, that it means that we need to put here sum n, and since we have four-dimensional space, it means n from 1 from 0 to 3. Okay, so but due to, again, I will remind, due to Einstein summation, usually we for Einstein summation we just don't use this notation of sum, but we remember about this. Okay, so and now what we will have for a Minkowski space. For Minkowski space, you can immediately see that since all components of the metric tensor is a constant, but here we have derivatives, it's understandable that all Christoffel symbols equal 0 for this Minkowski space. Is understandable? Are you here?
Yeah, understandable.
Yeah, it's obviously. The second, which is not so obvious, and I think we didn't do it. Just let me check. No, we don't do it. The second one, which is much more interesting, but much more simple, decided to choose. So we have 10 minutes, and I think we will be exactly in time. Let's consider the two-dimensional space. So let's consider dl, okay, dl square, as a, so I consider cylindrical, or not cylindrical, I will consider polar coordinate system. So it means that in polar coordinate system, yeah, so it means that I consider such a way that this xy, I will put this point, which is as angle phi and r, okay, polar coordinate system. And for in polar coordinate system, I have a square of the length as a dr square plus r square d phi square. Agree?
I agree.
No, it's so in this case, the metric tensor that we wrote it before, and now I remember this. So we have 1, and if x 1 equal r and x2 equal phi. So which is a component of metric tensor? The first will be 1, and the second is 0, and the second diagonal element r.
No, just R.
I think r square. Because again, look, we consider that the L square we can consider as the GAK, the XI, the XK. Okay, so for this two-dimensional, we have diagonal component as a G1 1, the X1 square plus G2 the x2 square. Agree? So it means that G22 equal r square due to the fact. It's understandable? Are you here?
Yes.
Yes, wake up. Now I will ask questions that you will wake up. So, and okay, I think when you will do the home task, finally you will feel it by yourself. So now I will show an example for, unfortunately, when we have a lecture in reality, we are doing all of this on the blackboard, and all of the students can train in front of, can train immediately. But we will try to do it also remotely way. Now we understand that we will have also the Christoffel symbols, and so I will put it like this. So this is R, 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 which is the same as gamma 1, 1, 1, since we call as the first coordinate as the R, so we can write like this. Also, we will have Christoffel symbols. This I will put as the index coordinate R, just to recognize it that this is related with the coordinate R, phi, phi. Okay. Also, we need to calculate phi, 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 and gamma phi R, R, like this. Together, it will be this one. Of course, we will also have phi R or R phi, and like this. So in principle, we can continue. As an example, to be in time, I would like to calculate the Christoffel symbol R, R, R. I just need to look on this expression. Okay. Everything very simple, because first need to understand this is 1.5. After this, I need just, instead of index, I need to write here, for example, instead of index I put R, and this is summation. Here should be D, G, R, N by, and here I need to put R, because
Because it's R is R.
yes, because R is the R. Yes, right. So plus D, G, R, N divide on D, again R, because R, this is R, minus D, G, R, R, divide again dr. After this, I need to put and here just for the help, I need to now to write it GRR equal 1, G phi phi equal R square. Okay. I also will remind that we have some relation between metric tensor that IN on GNK equal delta IK, which is 0 when K don't equal I and 1 when K equal 1 equal Y. So it just means that GIK for this case equal 1 divided on GIK. So the differences between covariant form and contravariant form, this is just an opposite. So you need to, for this one, consider 1 divide on the component of the metric tensor. So let's continue. So here we will have, we need to put, of course, the case. This means, again, we need to remember that this is sum n from 1 to 2. Okay, so we need to put here r instead of n, after this phi instead of n. But we can immediately understand that it will be survive only one case, when n equal r. Why? Because if you put here the index phi, j r phi equals 0, and since this is the multiplier, it will be 0. So for your home task, you can repeat it, you can do it much more careful way, but now to be in time, I would like to do it more quickly. So, and here I can write that
So
we have,
it's also equals 0.
sorry, say again?
No, it also equals 0 because here if we have n which equal r, we have 1 in g rn, sorry,
Yes, yes,
rr.
yeah, it will be
However,
0.
after that, we have just 3 constants.
Exactly, yes.
And also
So, but
that's
yeah, exactly. But I would like to write more general, you know, that everybody will understand. But you are absolutely right, because even if we can write here 1 GRR, and here we will have G. Let me see. GRR by R plus GRR by R minus GRR by R. So it will disappear. We will have 1.5 GRR derivative by R. And it will equal 0. So because due to the fact that GRR equal 1, and it is understandable that derivative from the constant will be 0. Absolutely right. So now let's, I have a few minutes, 1 minute. Well, let's find gamma r phi phi. So which will be not a 0. So I can write this is 1.5 GRI. It will be G phi, or we decided to call it n phi plus G phi n phi minus G phi n. So it will be survive only one sum. And so for if n equal phi, when n equal r, because if n equal phi, this will be 0. Okay, so I can immediately write that this is 1.5 GRR, but in this case I need to put everywhere G phi. I will write everything just to understand for everybody, plus G phi R phi minus G phi R. So it's understandable that this equals 0, this equals 0, due to the fact that we have only diagonal elements. So, and finally we will have 1.5 GRR is a minus G phi R. So GRR is unity, doesn't matter, this is covariant or contravariant component, so it's only one. G phi, so it will be d by dr on r square, okay, because G phi equal r square. And finally we have minus R. So you can see that in polar reference systems, the Christoffel symbol, one of the Christoffel symbol is not zero. Is not a zero. But again, it doesn't mean that the space is a curve. So this is the point. Okay, I can see that our time is over. So I will give you, yes, right?
I'm sorry, can I ask one short question? So
Of course.
can you show expression for Christoffel symbol, but in terms of partial derivatives?
This one.
Mm,
Or the general one, not through
general. So here we use the expression in terms of metric tensors. However, when we try to find expression for covariant derivative, we just changed some term which consists different partial derivatives, and we just call it Christoffel symbol. And I have some slight misunderstanding of this moment. And
no, of course we have expression for the Christoffel symbols through just the derivative from the coordinate from the x. Okay, x and x prime. Of course,
okay,
we have
yes.
it, but it's not convenient to use it. So because
okay,
because
but
to calculate the Christoffel symbols is much more convenient to use the metric and for the coordinate system.
Can we just see it?
You would like to
really
you would like to see this expression of
just
Christoffel
see
symbols?
this expression.
Yeah. Let's find it. Okay. So here you can see, here we obtain it. I can use like a green. So this one.
Okay.
So this is
all these parts, that's it. Okay.
Yeah.
So, for example, I cannot just and for this expression, how can we?
Okay, let's you
index
think
this?
about your question. I would like to give a home
Okay,
task, and
because
after
that's
home task,
that's
so?
only for last our home task, because here I just obtain much more simple construction, and I don't know, can it be Christoffel symbol or not?
No, but for the home task, you will use this expression which we obtained, and we obtained it honestly. Everything we did everything exactly this expression for the Christoffel symbols, which we obtained through the metric.
Oh, I mean in previous home tasks, which we already done.
For the previous, okay, for the
For
previous
the previous,
home task.
for this home tasks, it is understandable. Okay.
Okay,
However,
let's speak about the previous home task. We will speak for the next lecture. Okay, so I will put a special time for this to discuss. Is it right or not? I will look your solution, because I received many solutions. So and we will discuss it, because it needs time. So now I would like to finalize the home task. So the first, please obtain the others component of Christoffel symbols, all of them, for this case, for this space, which is for this coordinate system. Okay, so please write all the solution for Christoffel symbols for all indexes So I will not, you will understand which one you need to obtain. So this is, as we wrote before, this one, and also be sure that others are also 0. And the second, to train a little bit more, please also calculate, and it will be important for us too. Please calculate all Christoffel symbols for this space, for this interval. This is spherical coordinate system, dr square, r square, d theta square, plus r square sinus square theta d phi square. So this is, as you understand, this is spherical coordinate system. So, and try to obtain it for this case. So I just, for this, I will write that GIK. It means that it's 1 r square sinus square theta, okay? And all non-diagonal elements are 0. And with correspondent coordinates, which is r, theta, phi. So this is spherical system coordinate. Okay, do you have some questions about, and please find all the Christoffel symbols. As you understand, it will be not much, but more than for two-dimensional case.
Yes, but we have kind of 27 of them. Okay,
Yeah,
okay.
but many of them will be
not-
0 because you can immediately see that due to the fact that you have a diagonal element of the metric tensor, you can immediately see that much more of them will be 0. So don't be scared. It's not a lot.
And we must check that it will be 0 or just write that it's 0.
Okay, let's decide like this. If this is 0, you can write it's a 0. Okay, but what is okay? Find please non-zero component. Okay.
Okay.
So it will be better. Which is not 0. It's not a lot. To find no zero component. Okay. So let me make a screen of the present. Some question? No question. And please send me all of this before Friday. So as usual, I ask to send it during the week. So for this time up to Friday, or at least up to Monday. Okay, because we will use this solution for the Riemann tensor of spherical coordinate, because it will be the next home task. So if you don't have any questions, we will meet Friday.